enable me with the sharing screen.
Okay, just a second. I'll call them up.
I was host in the beginning and then PG and Council asked me to make them host. So now I can't do anything.
No problem.
I made them host, so now they have the access to this thing.
Yes, sir, you are good to go now.
Okay. So, so we are going to discuss the new dataset, which is MNIST dataset. It is a very basic and very popular dataset for desert recognition and other stuff. So before jumping to the dataset, I'll just quickly tell you that, again, repeat for everyone who is here new on the record as well, that I have put out the I've put out the this thing, which is your the data set as well as the competitions problem statement into your competition of ML channel on the Slack, and you will be able to go through the problem statement and as well as the visualization and stuff what we are going to, which we are learning from this lecture 1, 2, 3, and to the following, and to build a model. Today I will discuss some part of the basic mathematics, which will consist of linear algebra and matrix. So I hope you guys all know that, because we will not have that much time to go into the deep of the mathematics. But if you think I need to go to the very ground level of that, let me know. And then I can arrange it another day or something, or I'll just take it today itself, okay? But this is just to give you the foundation and specifically how to use it and the basic understanding of this thing. So we're going to go through the PCA. So PCA is principal component analysis. So let me, okay, so principal component analysis, and then over here. So for the principal component, okay, so we are going to go through the principal component and okay, let me see if I can write over it. Yeah. Okay, so we're going to go through the principal component analysis for the data set. So let's try to look at something from here. So let's say that these are the two axes, and you have some data points like, so bad data points. So you have some data points which is like this. So when I try to, maybe let's say that these are the two different data points, and I try to draw a comparison between them and try to visualize them through. So this is your X and this is your Y. So when I draw a line to maybe, let's say, to separate or to cover the data, I draw a line like this, right? So now the problem is this is if my line go like this, then it will be overfitting. I think you guys know that. And which is, and if my line goes like this, then it will be underfitting. So it's like not covering anything, and then it is the overfitting is when it is trying to cover all the points. So let's say that you have this point and you have to maximize the accuracy. Now you try to look at this point from this angle. Okay, you try to look it from this point. Now when you look at it, what you will see that every single line is falling on this line or this plane. So assume that this is a plane. So this all line is falling on this plane. So it will look like something this from this dimension, correct? Now if I try to look at it from this angle, let's say that this is the eyes, sorry for my drawing, but so at this point when I look at it, so everything which I will see will fall here somewhere, correct? So it will be somewhere, look like it is on this point or concentrated at this point, because this will all will become pointed to one point, and this will reference to another point, this will reference to another point, this will reference to another point. So this will be another plane. So now when I try to look from two different point of view, I can assume that this is one. When I'm looking from another dimension, look like it all the points lie on this plane. When I'm looking from this one, all the points lie on this plane. So this can be called as PC1 and this can be called as PC2. So like talking about principal components. So now let's try to understand. So it's like looking principal components is specifically to say that how does it look like from a different dimension. Okay, so it's to reduce the dimensionality of the data set and considering that how much variation we can reduce in the data, like we can retain the variation in the data set, but you can achieve the transformation of the axis for a better representation of the data set. So what's the bit of mathematics? So not going into very deep on this one, just try to cover quickly what are the different, how it is getting calculated. So we will cover, there's something important concept to know here is about this thing is that you have to, let's consider any data set D, or you have a matrix A. So in this case, we will be calculating the eigenvector, then eigenvalues, okay, and then covariance matrix. Now, how many of you are very much familiar with all these terms, eigenvector, eigenvalue, and covariance matrix? If you are familiar with it, then respond me on the Zoom in the chat itself by thumbs up. If you're not, just make some other face of smiley. Okay, many of you have an idea, many of you don't have an idea. So many of you don't understand the covariance matrix. So I'll just try to cover the basic of it, and then probably I can direct you to some of the points where you can learn it, or if you have doubt, you can ask me independently, not to waste the time of the whole class. So let's say that if you want to calculate the PCA, you will consider that your all data set. So you will have the full data set. Come on. And then let's say the data set has n dimension. So you will take the full matrix, which is n plus 1 dimension, into the consideration. You will ignore the labels. The second step would be you will compute the mean of the whole data set. Okay. Then you will compute the covariance matrix of the data set. Then you will have, once you compute the covariance matrix, you will compute the eigenvectors and eigenvalues. Okay. Oh shit. Come on, don't now. Yeah. Just a second. I will take my, this is charged. 1 second, please. Bear with me. My iPad is discharged. Okay. So try to understand. So we will have the eigenvectors and eigenvalues. Calculating those. iPads have the worst battery life and still they don't sell the charger with it. So now we have the eigenvectors and eigenvalues. Now what we will do is we will try to sort them we'll sort them, eigenvectors and values, into their in the decreasing order, and then we will have the we will form a matrix with n dimensions and k and k eigenvectors. Okay, so this is how it is going to be, and then we will use this to make the sample subspace. So now if I understand, so there are like, these are the basic steps that we go through: mean, covariance. So everybody know what mean is, so I will not consider this one. I'll just go with the covariance matrix and eigenvectors and values. I'll write in the formula here for you, and if you want to understand more into it and you have doubts you can ask me after the class, or if the majority of you require it, then I will explain it mathematically how to calculate them on a sample matrix. Okay. So let's say that to calculate the covariance matrix of any values, you will have, let's say, two samples, x comma y. You have the formula given as 1 by n minus 1 sigma I running from 1 to n xi minus x vector multiplied by I vector. Okay. So we compute the covariance of the two variables x and y using this given formula, and then we will have this specific. We will be having the specific dimension. Now for this, we will be calculating the eigenvectors and eigenvalues as well. So let's say that you have a matrix S of size n by n. Okay, let's say that you have this matrix of size n by n. So by the formula, we can say that S x equal to lambda x. Okay, this can be said. So we can say this one. So lambda exists as scalar quantity which can represent a specific matrix, so corresponding to a non-zero vector x. Now, when we calculate to determine the eigenvalues and eigenvectors of a characteristic equation, we'll calculate the determinant of this one. Lambda is equal to determinant of, these are very standard formulas, nothing new in it. A minus lambda I. Okay. And then we have to, so if we have a specific if we have a specific matrix, let's say that we have a specific, let's say that we take a specific matrix is equal to 2, 3, 4, 5. Okay, so this is a matrix that we try to design, and then we have the value lambda, so we multiply, so d lambda will be now equal to 2 minus lambda multiplied by 5. We are calculating determinant, so this is determinant of the matrix, 5 minus lambda minus 3 4 12. Okay, so this is how we calculate. Now, when you try to solve this, it will become a quadratic equation, and it will have lambda will have 2 values specifically to solve this specific equation. So, if you try to solve this equation, it will be you will just do the simple calculation here. So it will be in some factor of x lambda square plus y lambda minus, and then some values here. Right. So this is that what we are going to get from here. Now the question will be that if we have these values and then we can find out the lambda, so that lambda, the 2 values that we will be getting, will be considered as the eigenvalues. Okay. So they can correspond to the different. Sorry, they can correspond to different eigenvectors. And then you can have the 2 different eigenvalues, lambda 1 and lambda 2, and you can substitute them into the equation for obtaining the lambda, which is a minus lambda, which is s minus lambda I of x vector, and similarly lambda 2 will be s minus lambda 2I of x vector. Okay, and we will solve this for equal to 0, and you will have 2 different eigenvalues based on it. Then there is also concept of singular value singular vector decomposition here. So we also try to calculate this one, but the very basic formula for this one is also equal to A is equal to your sigma P transpose. So we'll be doing that step by step. Actually, if you want in the program as well to go for this one. So let's say that now we know that we have been able to calculate the compute the. So we computed the first the covariance matrix. Now we have calculated the eigenvalues and eigenvectors. Okay, so we have computed both of them here. Now we knew, so for on all these values, so now we will sort them into the decreasing order. Okay, and then we will have the final equation. So we can sample them, sample into new subspace. I'll just take a pause here for your questions. D is the determinant, and yes, we are solving the determinant of S lambda. Yes. Physical meaning of lambda. Lambda is a variable. It's like Greek letter, no?
Sir,
Yes. Speak.
yes, sir. Can you explain after after that you find the lambda's value? As after that, my internet connection was gone.
Okay, so lambda will represent to the eigenvalues, right? So you will substitute them into the equation that we discussed. Determinant of A minus lambda I is equal to 0. And then when you solve it for the lambda, you will have 2 different lambda values, and then so you will have 2 different lambda values. You will solve that, and you will get the you will get the different matrices, and then you will sort them into the decreasing order. Okay, and you'll choose the eigenvectors from this one. Okay, so And then you also do the similar vector decomposition. However, I think if many of you don't understand this calculation of eigenvectors and eigenvalues, I can show you how to calculate them on the sample matrix, but that will take time. So let's say if I write you something simple formula, let me see. Let me look for it. So if I write you a very simple formula to calculate the vector, so you can calculate the deviation or a variance covariance matrix, and and so if I try to calculate the deviation scores in a matrix, I think you guys must be familiar of something similar formula. Is if you have a matrix given A, like 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's say that you have this matrix given and you want to calculate the deviation score. So you will use just A, which is your matrix right now, minus 1, and then 1 of transpose, and then by A, and multiply by 1 by N. So 1 transpose, so 1 multiplied by 1 of transpose means you will take the size of the one vector here, which is something will be of the same of the size here. So your size is 3, right? So you will take the size of the 3 here, or you can just take a column vector, so 1, 1, 1, and then you will multiply with 1 transpose, and the transpose will be 1, 1, 1. And once you do the multiplication, you will get a 3 by 3 matrix of 1, 1, 1. And by this you can, by this formula, you will be able to get the deviation of the matrix. And on this basis of you can calculate the variance and the covariance matrix. Okay. Similarly, you can calculate the deviation scores in the matrices, which is just as simple as that. So it's matrix multiplication. Now, if so, this is basically a very basic idea behind PCA. To trying to so if you just want to understand the very basic steps and mathematics, you can dig into it. So you can always remember that you have you can always remember something like you have, let's say that, stop sharing now. Okay, so yeah, so we can always say that we can take the complete data set, and then of whatever n dimension it is, and then you can compute the mean of the whole data set, and then compute the covariance matrix of the whole data. So these are the steps that you can always remember. Compute the covariance matrix of the data set, compute eigenvectors and their corresponding eigenvalues, and this is the same eigenvectors and eigenvalues you will use in any translation on the data set in any other dimension as well. So if you are using any other dimensionality reduction technique, maybe for example in this one we are using PCA, we will be using t-SNE, and in signal subspace we try to use this one, CSP, common spatial pattern, to something. So we use the same dimensional, we try to change the dimension and the different projection into the data set. And that's how we break it down. Okay, so this is, if you I'll try to drop something maybe by the end of the lecture where I can direct you to some of the points where you can read it through and you will be able to understand this. However, if you even want to go there, I can actually tell you this one. So this is one of the articles of where you can see the visualization of the PCA, step by step. So I'm dropping out this link in your chat. drop it here. Machine learning lecture. Right. So I've just dropped it, the machine learning lecture. Right. So this is Sebastian Rashka, and then it has implemented the PCA step by step. So you will be able to understand what I was talking about in the terms of covariance matrix and other stuff. Since we have a short period of time, I will not be able to cover everything. But if it is required, I will cover it. So you don't need to think that I am not going to help you in understanding anything. But I think this is basic mathematics, and many of us understand it. So I'll not do those things. Okay. So now let's go to the data set and try to understand. This is a new data set that we're considering. So we have an MNIST data set, and we have to compute the PCA. So again, we are using the NumPy as NP and Pandas as PD. And we have matplotlib, pyplot for PLT. We are trying to read the data set, which is MNIST data set. It is a very sample data set in which you have the digits as an images. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, till 9. And then, so all these digits, so you will have 10 classes. And so here you can see that you have data set. So I import the data set.
So Sujit, can you increase the font size?
Oh, sorry. I'm so sorry. Thanks for reminding. Yeah. Is it visible now? I hope so. So now we have this data set, and we try to look at the location 0. We have the labels. So we see the labels of the MNIST data set as label and drop them. Now, again, we try to look at a specific image. So this is how one of the plots look like for a 0. It is 28 by 28, and try to look at this plot. It'd be great to see a lecture where we apply ML related techniques to something that is not image processing. We're not doing image processing here, honey. So whatever we are going to do can be translated to another data set as well. That's why in your Slack, in the competition of ML, you don't have an image data set. You have just a normal data set, and you will be using the same technique to get it there. So if I tell you, if it makes you very much difficult to understand, so let's say I give you a very basic example of a PCA or something. So imagine that you have a large variables assigning to a specific classification or a specific point, right? So let's say a very specific term. For example, you have 206 sensors or 200 sensors deriving the same information, right? Same information related to different to some activity, and then you try to do a classification here. So here you have a very huge dimension. Your dimension is the 206 number of features here, which can, so all of these sensors can be treated as a new feature. Now, all of this is not going to contribute positively for your classification. So machine learning purpose is classification or prediction, right? So your prediction, so all of them is not necessarily going to contribute to a positive, positive classification or positive prediction. So it is very important to understand which of these features can help us to understand the data or the model much better. So what we do is we take all of this and project into some other sample subspace, okay? And then we try to look at it from those variables or those points, that how we can reduce these features. Let's say we take only 2 features where there is a maximum variance in 2 classes. So now if there is a maximum variance or maximum separability, it will be easy for us to just draw a line in it, isn't it? For example, let's say that you have heard about deep learning technique like CNN or something. So they are complex equations to neural networks mechanism to separate out the two information in the data set. Let's say that if there is a data set, and if I transform into some other space, let's say if I just take a log of some data set, I transform into some other space. Now, if I try to then compare the two different variables, it might be a case that it might be just separable by a linear line. So this projection, this is actually a projection, no, in different space. This projection is very helpful. It can be applied to any data set you come across in the machine learning. It is just to reduce the number of dimensions you have. So here we have this one. So we got to we saw the implementation. Now let's say that we have 20,000 data sets. We want to just pick 20,000 data sets. And then we have the sample data. So now data pre-processing. So what we are doing is standardizing the data. So today it's a bit of a theory. After that, we are going to jump on the models to tell you how to train the models and other stuff as well. And then you have the data set to try on yourself ongoing. So you're using the sklearn pre-processing or using standard scalar to standardize the data and transform it, right? So you want to do that. Your shape is 784 because your data size was 28 by 28, if you remember from here. And 28 square is 784. Okay, so here we have the 28 by 28. So if I flatten it out, it will be 784. Now, since this is that one, now we try to calculate the covariance matrix by using the mathmul. So NumPy has a method called the mathmul, which means a matrix multiplication, right? So what you are going to do, you are going to take this sample data, which is the standardized data, take the transpose of that, and take the sample data itself. So you try to do the matrix multiplication here, and then you will get the covariance matrix. The size of the covariance matrix is 784 by 784. I just explained you by taking your unit vector, how we do the transpose multiplication, it will transform the size. Okay, so now from these, we are trying to find the top two eigenvalues and corresponding eigenvectors for projecting into a two-dimensional space. So let's say your data can be highly dimensional. That is our scenario. So we have 200 features or 300 features in some other areas or something. We're trying to minimize it so that we can represent that data into a 2D subspace or two-dimensional space, right? So what we're going to do is we are going to use the SciPy library. I'm again explaining the only methodology because I think that I've explained the mathematics behind it, showing the implementation. If you want to go to dig deep, you can just ping me on this one, and then we can go for dig deep. Digging deep into the Pca or any dimensionality reduction mathematics. So we have to calculating the values and the vectors. We are using the SciPy library itself to calculate the eigenvalues. So we have covariance matrix that we calculated and eigenvalues. So once we go for that, we check the shape of the vector subspace and then take the transpose of the vectors and then update the vector shape. Okay, so you have specific values and vectors. So now you have two. What do you mean by features? Can you please explain? So features. So which features are like the attributes? No, attributes which will tell about a specific class. Let's say apple. Apple has features like it is color. So color of apple is red. That's a feature. Some apples are green. That's another feature. So the shape is round. The height of the apple 5 centimeter, and then you have more circular on the top, less circular on the bottom. So these all things which are the attributes can be considered as single feature. Okay, can be considered as a specific feature. However, this is very important to understand as well that let's say it is related to a specific object. Okay. Can please consider spend 30 seconds to module that imported and TS, please look into it. So now, when you look at this feature, in this case, you have these features. Let's say that I want to implement my same machine learning techniques into some other data set. Let's say that I work in the presently working in the domain of neuroscience, right? So if you have heard of the term like EEG or MEG, right? So EEG is electroencephalography, MEG is magnetoencephalography. So in EEG, you can have 128 channels or sensors on your head to collect the specific data of neural signals of your brain activity. Similarly, in MEG, we have 306 sensors. So these 306 sensors can be treated as single, individual features as well, which are telling you information about the specific activity ongoing in your brain, to classify them into different vectors, into different features. So these are the features. Now 30 seconds, a module that imported and to do what it is imported. Your English, I don't understand. I think I just go ahead with imports. So what we have imports here, you have the module anyway, isn't it? We have considered all the imports and other stuff in the beginning. So it is just very straightforward. And I have also taught you in the beginning of it how to look for a specific module and their methods, right? So we are using NumPy, Pandas, Matplotlib. Then we are using SciPy. And then we are using eigenvalues for eigenvectors calculation. Then again, we are back to Matplotlib. Okay. And so here we have calculated the eigenvalues and eigenvectors here. And now, now you calculate the projecting the original data sample on the plane. So we do the simple matrix multiplication of vectors and sample data t, and we get the new coordinates. So this is it. So now, when we look at the new coordinates and the labels, so they are stacking arrays in sequence vertically. Now data frame. So this is the data frame that we have got. Now you see this is the first principal component, this is the second principal component, and their corresponding labels, which is 10, 00, 10, 4. So these are the specific integer of the class that are going. Okay, so this represents to digit 1, this represents to digit 0, this represents to digit 1, this represents to digit 4. That's in the MNIST data set. If you just maybe just go on Google and type MNIST, you will get a description about all this data set. But this data set, in a very blunt terms, consider that it is a data set collection of all the 28 by 28 pixels of all the integers, not integers, from the numbers 0 to 10, sorry, 0 to 9. So we have first principal component, second principal component, and their label. Now we try to plot this thing, okay, the first principal component and second principal component. Sorry, I did not calculate it. So now once we do the principal component, so now you see this is the representation of the first principal component, second principal component of all these data sets. So these are the different classes. Now they all seem overlapping to each other, but some of them will be very much separable as well. They might be separable in the specific plane, right? So this is how we have done it step by step in terms of calculating the covariance matrix and vectors and values using PCA. Okay, so now we have scikit-learn. So now how we can use it in a single step in just scikit-learn is that we can do a decomposition.pca. So in scikit-learn, you have a method defined as decomposition. When you call decomposition.pca, it will call up the values in PCA. And then we have the number of components that you want to define, how many principal components you want to calculate. You want to calculate 2 components, 3 components, 5 components. You can calculate up to n components, and where n are the features, maximum features. Okay. So if you have say 200 features, you can get 2 components as well as 4 components. But you will always visualize this thing when you calculate the principal components and try to look at the variance. It will decrease from principal component 1 to the n. It will be in the decreasing order always. So when you calculate, define, so if you take, so if I say number of components 2, so it is like projection into a space where they are trying to pull apart from the 2 vectors here. So if I plot PC1 versus PC2 for 2 specific data, 2 features of the data set, we will be able to see some sort of separability, which means that if there is a good separability, it means that the data is very much separable just by taking 2 principal components, and we are covering the maximum amount of data in that case. So then we do the PC. So we decide the number of components here, which is 2. I told you can go up to n components. Then PCA data is just doing the fit transform into sample data. Okay, and then you will reduce the shape of the data set, which will be reduced to 2 components. Previously you had 784, and then it is reduced to 2 components. And then you virtually stack them, and then here you have the PCA data. So once we look at that, it takes some time to run, and then In just one step, we will be able to do all the things that we did individually in the beginning, which is doing the matrix multiplication and other stuff, the steps. Okay, so here we got the size of PCA reduced, and now once we see this, so we have the same principal component, which is first principal and second principal corresponding to different labels as we have seen before, the way we calculated. Okay. This is exactly same. Now, so this is about PCA. So it is used for dimensionality reduction. Now, similarly, you have a task here as well. So you can try with 42,000 points and see how it goes. Now, similarly, you have t-SNE. So t-SNE is also used for dimensionality reduction. So you can you also call it as distributed stochastic neighbor embedding. Okay, so this is also used for differentiating the data into a different. So it's like it is like a neighbor embedding where you try to visualize the separation, in the data set. Now, for this one, for a clear visualization, I have found something, and I would be happy to share you that, which is this thing. Stop share and then screen 2. I think you can see this, which is how to use t-SNE effectively. Now, t-SNE has different components, which you can say that you have different parameters. One is points per cluster, one is perplexity and epsilon. So once you go ahead with the t-SNE techniques, so this one you can always look at this blog, and it will help you to understand the importance of hyperparameters as well in separating the two data set and how it is how it will help you to change the data set. Okay, so in just like perplexity is like the attention for the data set, how much global, so how to balance the attention between local and global parameters. So let's try to visualize. So let's say that this is the point per cluster is 100, and this is the data set. So now as the number of steps keeps on increasing, you will see that the data set is trying to solve itself, and ultimately you will reach a position where it can be separable just by a single line. Okay, similarly, if I change the perplexity and then we see, okay, so you can play around with the variables hyperparameters, and you can see how the values keep on changing. You see, so now if I look at it, it is very good suitable for us that if I keep the perplexity around 13 and epsilon to 2, it is very much separable just by a simple linear line. So I just need to draw a linear line to separate out these two different features. Okay, so similarly, you have different data sets, and you can keep on changing the number of points and steps. So all of these are dependent on this one to make the data separable and other stuff. So you can play around with this thing. Similarly, we will just try to have a look at how. So this is this website. I think distill.com 2016. So I'll just drop this in the Slack. Okay, I dropped it into this in the Slack. So now so this one is telling you the information about the t-SNE, how you can, there are different cluster sizes and different plots. So how the improving, changing the parameters, how it is changing and making it more separable. So distances between clusters, and then how you have random noise, changing variables, and then shapes and sizes, topology. So there can be different topology. For example, a ring into the ring. scenario as well, and that can be also changed into a different subspace, and then that projection can be separable. Like this one I was talking about. So you see, when you try to change it, you start separating it up. So you can try these values out just for fun and see if you still have any. So these are like just simple hyperparameter tuning. Okay, now let's try to look at it from our perspective, from the in the scikit-learn in the Python. How do we do that? Okay, so in Python, to calculate to use t-SNE, we just use the sklearn.manifold, and in that we import the t-SNE. So it's the same data set that we were using, MNIST, the sample data set we have along with the labels. Now we try to compute a model here where t-SNE, number of components we are defining, which is 2, random state is 0. We can change it as well. And then you have the t-SNE data. Okay, it'll be slow. So for t-SNE in the scikit-learn, so this is how to see how we use t-SNE modules in scikit-learn. So for that we will be importing the t-SNE module from the sklearn.manifold. So as you can see on the screen, you have the data set which we have used just before now. This is data set, and then you have the sample data which is 0. So we are taking the first 2000 data set and similarly 2000 labels, right? Then we try to compute the model is using model with output using the t-SNE method that we have imported, defining the number of components to be 2 and the random state to be 0. Then we calculate the t-SNE data and use the model which we have created to do the transform. So model.fit transform data. So this will do the data projection. Okay. So now we have the t-SNE data and we do the same virtual stacking of t-SNE data transpose and their labels, and then taking the whole transpose of that. And then we have the t-SNE data frame. Now, when we plot it, you are able to see this distribution. We saw the same distribution using principal components. Now, which one of them will be easy for you to separate? For me, it would be this much easy because you see the cluster formation, which is very much clear. So when we try to do the different projection, right? So when we go and click on this one, and if you plot, so we have this difference visualization in the terms of Pca and in terms of Pca and t-SNE, right? So for this one, I'll just also take you to one more point, which is let's quickly check at this thing, which is sklearn t-SNE method. Okay, so if you go on the way I have suggested you before, check the method arguments and their clarification. So if you look at sklearn.manifold, import t-SNE. So you will just go to sklearn.manifold.tsne and you will be able to see all the different arguments there. Okay, so you can have number of components, random state, even perplexity, early exaggeration, learning rate, iteration, and other stuff. Okay, so all these things can be done. Okay, so you can do all those things. So that what happens if we set random state to 1? Random state actually is just to create a random instance, right? So it's like random number generated. You can change it to anything, but generally why we use random state is to regenerate the same result. So what will happen sometime in machine learning or deep learning when you will be start training, and if you don't fix the randomization, then you might get a result, but when you try to reproduce it, so until unless the model picks up the same random state, it is not going to give you the exact same result. There will be minor variation. That's why in every model computation or anything that we try to do, we try to declare a random state. which can be any integer. It doesn't matter to be specifically 0, 1, 2, 3, anything. Okay, it can be anything. So if you have all been to the sklearn.manifold.t-SNE, so now if you look at the arguments here, so we have the number of components, okay, then we have the perplexity I have just shown you, then early exaggeration, learning rate, number of iterations, without progress, minimum grade normalization, matrix, initialization, verbose, random state, method, and angle, and jobs, number of jobs. So don't go into all of this, but I can tell you that because you have seen on that blog that I've shown you before, that how the perplexity was changing it, as well as the epsilon values were changing it. So it would be you can try to play around with this one, and you can see that the perplexity is related to the number of nearest neighbor that is used in other manifold learning algorithms. So you can use different values between 5 and 20, and then you will have a different presentation. So let's say that I want to use the perplexity here, and I want to define it to 5. Okay, and then again I do this. What happened? Sorry, that. And then, so now it will be a different observation. However, it was your task, not mine. So now you can do the number of iterations as well as perplexity change and see how it behaves. Okay, we'll just see how the output of this one. So now we have a different distribution from before. Okay, if you include the number of iterations as well, you will have a different distribution. So specifically now to summarize both of the things, PCA and t-SNE. So you can say that these two are basically dimensionality reduction techniques, which are very important in the machine learning domain to reduce the number of dimension in the data. Number of dimensions generally correspond to the number of features or attributes for the data set. So if you have a very huge amount of features given for a small data set, your data might overfit. But when you train or underfit, it will be very difficult to train such sort of data. Additionally, it will create a numerical imbalance between the data itself if you have a very high numerical instability between the data, depending on the chart. For example, let's take an example data set, example here in the domain of data collection. So let's say that some of you work in the domain of medical science, or let's say in economics, right? So what will happen is if you have a very huge demographic and different features for the demographic, and you have just a sample size of 100, and you have a demographic of something around 300. Now you see there is like 300 features to determine the hundreds of sample space. So it would be very difficult for us to create a. It would be very difficult to train a model and attain the higher accuracy in order to do that. So there can be a provision in which we project all the features into a different space, and we will be able to classify the data better and reduce the dimensionality. Reducing the dimensionality will also help us in decreasing the time steps, as well as the training time, computational complexity, and other stuff, because it will be useful in those scenarios. So we have these things here, and then I have, so you can give it a try, and then you can see the questions if you have. From tomorrow, we will try to go ahead with the basically the model training and other stuff. Okay. Right. So this would be it for today. And
There's one question about standardizing the data. So You can continue
Okay.
asking more questions.
So
If
standardization of the data is specifically, I'll tell you. So one, there are different terms you're going to hear since once you start dealing in the machine learning. Is one is standardization, then the other is normalization. So basically, what we try to do here is trying to scale the data between minus to 1 or normalize the data into the different. So, like for example, why it is important. So let's say that you have two different distributions and they have a huge variation in the distributions, right? So if we don't normalize the data, it will be difficult for us to train the model because of the huge variations here. So that's why we prefer to normalize the data. There are different methods how we normalize the data. The basically what we use generally is we always generally calculate it using the mean and the variance. So we have G score and other stuff. For using the standard scalarization, we try to use the min max scalar as well to scale the data between a specific range. So it is just like you can consider like interpolarization to reduce it. Okay. So try to depending on the data set, if your data set is going negative, for example, signals, if you try to, because signals can be negative as well. So you have, when you try to normalize it, you try to normalize it between -1 to 1. In other data set, for example, image, you try to do it between 0 to 1. And when you, so that's called the normalization. And then when you try to standardize, you have similarly, you have a variation and which will have a mean 0 and standard deviation to 1. Can we do multi-core processing of data, for example, to speed up the t-SNE cell code? So I don't understand what do you mean by multi-core processing of data. If you are expecting an answer in the terms of to see how it will behave or change in terms of multiple threading, then yes. But if you're using different cores, if you're talking about in the terms of hardware, we can always use parallel programming for multiple threading. Yes, you can use more process threads. And for that, I think you will be very much aware if you're asking this question, then I expect that you must be knowing about batch sizes and other stuff. So you can train on the different small subset of the data and try to append them and append the processing out of them and make a whole transformation to data as well. So this is something similar that we have seen in TensorFlow or something in deep learning, where we try to do this thing. So any hyperparameter optimization, can be taken to the different cores or process of threads. That is always possible. Next question. Can we apply a common factor to all the data set for standardizing? If you are doing the same comparison, you will try to bring down to the standard scale common factor. If you apply a common factor, then you're just scaling up the data, isn't it? So if I have a specific data set, let's say that you have a sin x, right? When you multiply it by 2, 3, or 4 to any of the variables, it will scale in the same factor. There can be one more approach which I just came thinking here. So let's say that you're trying to normalize the data, and for normalizing the data, obviously you calculate the mean and the maximum and the minimum, right? So you calculate the normalization using x minus x minimum divided by x minus x minimum. So to normalize when we normalize the data, if you are using the two different data sets acquired from the same system for two different sessions, then you will have to take the same mean and standard deviation to calculate the normalization as well. So you will not have, generally, we don't intend to normalize the data separately in those scenarios. Okay. Okay, and there is one more question. Actually, somebody has put up on Slack that I have a few doubts in the last lecture, mainly in calculating variance plot. Could it be possible for you to give 10-15 minutes for doubt clearing? So yeah, so Akansha, if you have a specific question related to variance plot, you can write down to the TAs in their personal messages even, and they will reply to you. Or you can just ping me as well. Like I'm known on Slack as Lelucius Britannia. You can ping me in as well, and then I'll be able to tell you the interpretation or something else. Okay, so I think today's time is anyway up. So we will be closing it, and then we will be jumping on to the understanding models and model training. Apart from that, there is a point here to all of you that if you are interested in understanding the mathematics or something like that, because I was told that you guys, some of you are from computer, some of you might be from computing, some of you are from other domains as well. So I don't know how much standard mathematics you guys understand. So we will be using, so any model explanation can go up for like simple, like we are right now using simple linear algebra and other stuff, but can go to calculus and other stuff. So if you guys are comfortable with it, I will try to cover a simple mathematics which can be explained in the simple language, and then if you try to, if you can go dig deep in terms of, I'll give you the links like I have given you today to understand things and go ahead to do your research, or you can also ping me to explain you all of the things on a sample matrix or sample calculation. So I'll do a stepwise calculation, and you can ask maybe your answer to arrange, depend how many students are there. If you have 50% or more have the same doubt, I will repeat it or explain it in terms of matrix multiplication and how this all steps have been calculated in terms of eigenvector stability. This will be followed up for the next class in other models as well. But this one is specifically to tell you that if you have any data set, how you can use the data set for making a model and make a better interpretation. Okay, so that would be it for today's class. I hope everybody is fine. So then I'll see you after tomorrow. You have this sheet to practice ahead and change the data set. I have also updated, given you a new data set and other stuff, which is not image. We'll be doing that. In the coming data set, we'll be going for classification as well as regression, all those things. So we will be able to look at those things. Okay. All right then. See you. Bye bye. Have a great day.
Bye-bye.